Recently, a new type of motorsport has emerged entitled autonomous vehicle racing. In order to promote the research of such topics within an academic environment, the Formula Student Driverless Cup competition was created. Making a car go as fast as possible is no simple task for a human and certainly not for a computer. Several modules need to be built in order for the car to perceive the environment, estimate its states, plan a path, and finally control the car. In this work, only the control module will be addressed. The first necessary step is to choose the controller. Due to its previous successes in the field and growing popularity, the model predictive control technique was chosen, from now on referred to as MPC. MPC is an optimal control problem that tries to predict the near future with some model of the system and based on a cost function comes up with the optimal inputs. Here we can see the predicted trajectory of the car in the next 2.5 seconds showcased with the red cylinders. In this work, the developed formulation is based on the contour problem, making it become the model predictive contouring control, in short MPCC. This formulation tries to minimize the lateral distance of the car with regards to the centerline and maximize the velocity at which the path is being traveled. This allows the car to generate its own racing line. In order to further enhance the capabilities of the car, another module was developed called torque vectoring. Torque vectoring tries to optimally distribute the torques in each wheel in order to enhance the cornering capabilities of the car. Two approaches were developed. The first one, a linear time varying MPC, was used, but since these dynamics completely change the behavior of the car, it needs to be modeled inside the MPCC. Modeling an MPC inside another MPC can be a hard task and therefore a data-driven feed-forward controller was developed. With these algorithms, the car attended 3 major competitions. Here we can see one of its best performances in Formula Student Spain, where the car can be seen reaching lateral accelerations of up to 1.5 g. Still, for really high accelerations and speeds, the first principles model starts to perform worse due to unmodeled dynamics and parameter uncertainty. In order to tackle this issue, a neural network is introduced that learns the arrows associated with the first principles model and complements it. Such approach is now called learning-based MPC. Looking into the results, it is possible to see how much better the augmented first principles model with the network is at predicting the future, surpassing the conventional first principles model in most of the used metrics. When testing in a high-fidelity simulation, it is possible to see how faster the LMPC is when compared to the MPCC, and also to the previous team approach, a geometric controller called Pure Pursuit, showcasing that a better model does lead to better control actions. Finally, the last experiment shows the capacity of the network to adapt to unknown situations. The torques of each motor are decreased, and after gathering data from one lap, the neural network is trained, originating the online NN. As it can be seen, by incorporating this data, the car manages to correct the model online, improving its capability to predict the future, and consequently, the lap times. All in all, the MPCC formulation helped the team secure first places in Formula Student Portugal and Formula Student Spain, and a third place in the biggest competition of the world, Formula Student Germany.